Everybody, Thrasher again here. For this page number 15, I'm talking about how to answer these conceptual questions regarding conservation of momentum. I'm not going to write out every little thing, but I'll hit some main ideas, and maybe you can hear how to practice explaining these. And then, of course, obviously, if some of these problems were a little challenging, I can talk through how I approach these. All right? So problem number 1, you're stuck on a frozen, frictionless lake. You got to get to shore. You got to somehow get over here. How are you going to do that? Remember the idea of conservation of momentum. Whatever you have in the beginning is what you have in the end. It says that you started just standing here. So your total momentum in the beginning is 0. So if you start with 0, you need to end with 0. So imagine you took your backpack, that's my backpack, and you threw it to the right. Well, that means all of a sudden you have some momentum to the right. But in total, I have to get back to 0. So if you throw your backpack to the right, what has to happen to you? You have to move in the opposite direction. This is the classic recoil problem. Your initial momentum was 0. By conservation of momentum, it needs to end up at 0. So if your backpack has momentum one way, you must have momentum in the other way. Okay? That's the main idea. Moving on, problem number 2. Problem number 2, to be honest, might be a little challenging, and it kind of depends on your interpretation, and there's an easier approach, or you could get a little more in the weeds, but we'll try not to do that. In the beginning, right here, I have this firecracker hanging still. So what is its momentum in the beginning? It's 0. It's starting off at rest. So if momentum is conserved, what should the final momentum be? It should be 0. Now, this is not a trick question. I'm not looking for like, well, after it blows up, the pieces are on the ground and it's not moving. No, I mean from here to here, before the explosion to immediately after. When it hits the ground and all that, those are outside forces. We're not dealing with that. We're talking about momentum conservation, and you can apply it. Remember, momentum depends on direction. So you might think like this little piece right here, it has momentum, because remember, momentum is always mass and velocity. This piece right here is moving up and to the right. It has momentum. How could I possibly get back to a momentum of 0? Well, if I have another piece that's moving in the opposite direction, it could cancel out. Likewise, right here, this piece is moving up and to the left. Well, maybe this piece right here, it's moving in the opposite direction. It's canceling that momentum. In total, the overall momentums of all the different pieces are going to cancel. So yes, momentum is still conserved. We've been looking at examples where bombs were just breaking into 2 pieces because it was a little easier. But momentum is still conserved even with a messy, large, complicated, multiple fragment bombs. Momentum is still conserved. It's just, to be honest, it's a little tougher to analyze. But again, for this question, if you're talking about that the momentum of the initial momentum was 0 and the final is 0, and that you have pieces where momentums are canceling from one another, that's the general idea, okay? Next one, number 3. Number 3 really helps with the picture, even though a picture wasn't included. All right, and again, it's based on do you recognize the idea of what's the momentum in the beginning and what's the momentum in the end. So 2 objects collide and one of them is at rest. So let's imagine, again, billiards is a good way to kind of think about these. Let's say I have one billiard ball. Sorry, that's the best I can draw. It's moving to the right. Does it have momentum? Absolutely. And it hits just another stationary billiard ball, because again, one of them is initially at rest. Well, okay, if momentum is conserved, the momentum in the beginning, and then remember they clack, they hit, my action bubble needs to equal the momentum in the end. Now there's no numbers here, but what direction is the initial momentum? It's to the right. So what direction should the final momentum be? To the right. So if I need to have a momentum to the right, can I have both objects that are at rest, that are not moving? Because that's the scenario letter A is posing. Is this possible? No, that's not possible. Because this is implying that the momentum is 0. But the momentum needs to be something, some number to the right. So for 3A, it is not possible. This would violate, unless there was some interfering force, this would violate conservation of momentum. Let's jump down to letter B. Let's use this same scenario. So again, I have this one billiard ball. It's moving to the right. There's another billiard ball stationary. Is it possible for one of them to be at rest after the collision? So I have my action word. I have my clack. I have my billiard table again. Could I have maybe something like this where one is at rest and one is now flying? Does this work? It does, Because what was my momentum in the beginning? The initial momentum was going to the right. It's not zero because this object here is moving. This one's not moving, so the total momentum is to the right. Here is the total momentum, P final. Is it to the right? It is. This absolutely could be a scenario. It checks out. Maybe if you've ever played pool, sometimes when you're shooting pool, the cue ball, it slams into the object ball and it seems like it comes to a dead stop and the object ball goes flying. This is allowed because this still matches conservation of momentum. If you're playing pool, you can't have both balls come to a stop immediately after the collision. Maybe after a few moments because of friction, hitting the rails. But remember, those are interfering forces. Utilizing conservation of momentum, this is not possible. But this is. That's fair. All right, moving on. Next question is asking, a car is parked, it has mass, does it have momentum? This actually isn't really a conservation of momentum question. This is just basic momentum. Remember, momentum is equal to mass times velocity. A car absolutely has mass, but if it's parked, if it's at rest, what's its velocity? Hopefully you say it's zero. So does it have momentum? You could probably answer this one of two ways. You could say no, it does not have momentum because the velocity is zero. Or it's okay if you said, yeah, sure, it has a momentum of zero. That'd be okay. That's kind of the same thing. But make sure you explain it. If this was a quiz question, be like, all right, Thrasher, this is what momentum is based on, mass and velocity. Even though the car might have mass, it's parked. Well, therefore, the momentum is nothing, or it has no momentum. Okay? Number 5, superhero question. But this is the same question as the recoiling gun. It's the same question as the person stuck on the frozen frictionless ice. In the beginning, before the person has thrown, what's the momentum? In the beginning, it's zero. So after, and the picture is showing after, this boulder, this rock is flying to the right. Does it have momentum? Yeah, it has momentum to the right. But if the final momentum, assuming it's conserved, assuming it's staying the same, if the final momentum is zero and the rock is moving to the right, what does my superhero have to do? They should be moving to the left because I need to have some positive momentum. That's the only way I can combine it, is to add some negative momentum to end up with zero. And why do I need to end up with zero? Because that's how I started. The initial momentum was zero. So by conservation of momentum, if the boulder, if the rock has momentum to the right, the superhero needs to have momentum in the opposite direction. That's what's important. They're in opposite directions because that cancels. That's the kind of explanation you need to be able to write down to get a 4 on my quiz. All right? Next one, number 6. If I scroll down a little bit, I'll have number 6 here. It says 2 cars are driving on the road with the same momentum. Okay, again, this is not a conservation of momentum question. This is just a basic momentum question. If they have the same momentum, so 2 cars have the same momentum, but they have different velocities. How could I have the same momentum but have different velocities? Well, momentum is based on velocity, but it's also based on mass. So, I don't know, I'm just going to make up some numbers. Maybe I have 10 equals a mass of, I don't know, let's say 2 multiplied a velocity of 5, right? Mass of 2, velocity of 5, a momentum of 10. I could also have a momentum of 10 if my mass was 0.5, again, I'm making up numbers here, and my velocity was 20. Oh, here's a perfect example. I have the same momentum. I have different velocities. How is that possible? Because I had different mass. How would I write this down? Momentum is based on mass and velocity. So if the mass was different, even if they have the same momentum, they could have different velocities. Okay, there's an explanation. All right, number 7. Number 7 is getting back to some conservation of momentum questions. Now, to be honest, on your printout, I probably should have had some little action lines right here. You might want to draw that on your paper, but there is this arrow. Okay, these arrows are representing velocity. It says one of these 3 is not possible. It makes at least the least amount of sense. All right, how to approach this? There's no numbers. Remember, momentum should be staying the same and direction matters. If I started with momentum of 0, I should end with momentum of 0. Look at letter A. I start with momentum to the right because this object has right momentum and this object, it looks like it's at rest. So it's the total. momentum to the right. So in the end, does it look like I have momentum to the right? It does. Again, I'm not talking about velocity, I'm talking about momentum. Letter A seems plausible, okay, because before I have momentum right and after I have momentum right, and it seems kind of like the same, okay? How about letter B? Letter B again starts with a big momentum to the right, or at least, excuse me, as I'm yawning, this object is moving right and it's moving a lot because of these action lines. This one's at rest. I start with momentum right, I end with, oh, what's going on here? Could this one have momentum to the right? To be honest, it is possible, because remember, P equals mv. This is a really large object, or at least it looks bigger. So maybe it has a really big mass and it has a smaller velocity. It's still possible for this to have momentum to the right. Letter C, well, okay, it has some momentum to the right. What's happening here? Wow, look at this. This object with way more mass has way more velocity. Does it seem like it's the same amount of momentum? It doesn't to me. I don't actually like number 17. Number 7, as is, won't be on your quiz. I'd make it more clear, because all of them kind of have momentum to the right before and after. But in my opinion, C makes the least sense, because it looks like I have way more momentum. But I don't think I'll put this on the quiz, because this is a little less clear. Maybe I'd have an example where they start to the right and they end like to the left, or maybe they start to the right and they end with 0, and then they start to the right and they end to the right. Okay, it would be a little more obvious. All right, but you could compare the momentums before and the momentums after. For problem 7, I didn't do a good enough job differentiating. So don't worry about this question as is. But again, if you can figure out the momentum before, and maybe that's just direction, you should be able to say that's the same direction, if momentum is conserved, that's the same direction as the momentum after. All right, but let's kind of skip number 7. All right, now let's keep going. All right, granny time. If you haven't read this question, hit pause and read the question first, and then come on back to my video. For letter A, it's asking to fill in the blanks. Let's do that, okay? Fill in these blanks. Granny has a mass of 80 and a velocity of 3. What's the momentum? Momentum equals mass times velocity. In your calculator, what's 80 times 3? It's 240. I'm going to leave off units right now, but it'd be kilograms, meters per second. Okay? What's the momentum for Ambrose, this kid? Well, the mass is 40, the velocity is 0. 40 times 0, that's 0. Okay. So the total momentum is 240 plus 0, that's 240. Maybe I'll write the units here just so you remember those units. 240 kilograms, meters per second. Now, letter B, Granny grabs Ambrose, right? That's what the picture shows. All right, circle the correct answer. After the collision, does Granny's speed increase or decrease? Well, we could prove this mathematically, but think of a scenario. You're moving, or maybe you saw this with the lab. If you grab something, if momentum is conserved, but all of a sudden have more mass, if the mass goes up, the velocity should go down. Or maybe you just thought of this real world. If Granny was sliding, then grabbed something heavy, it seems more likely that their speed, their velocity will go down. Letter B, this first one, this sounds a little tricky. I'll probably not ask you that directly on the quiz. The second part is way easier. You should totally be able to answer this one. Does Ambrose's speed increase or decrease? This one's easy. They start not moving. So what happens to Ambrose's speed if they were snatched up by Granny? It should totally increase. This question is totally fair game. This one's a little trickier. I won't answer, or I won't ask that one on the quiz. Okay, let's keep going. C, after the collision, what's the total mass? Well, add the two masses. What's 80 combined with 40? That's 120. Okay, 120 kilograms. I'm going to switch to red. Now for letter D, use conservation of momentum to find the speed of Granny and Ambrose after the collision. This is going back to some of those tougher math problems. Show some math work. So let's use conservation of momentum. The momentum in the beginning is the momentum in the end. In the beginning, who had momentum? It was just Granny. This is the momentum in the beginning. And it was only Granny. What was Granny's momentum? Oh, it's 240. So the momentum in the beginning, I'm going to scroll back down. It must just be Granny, because Ambrose wasn't moving. What's the momentum in the end? Oh, I don't know. I tried to give you a little hint right here. Remember, Granny is holding on to Ambrose. They're together. So, yeah, P equals mv, but the mass is now Granny plus the child, plus Ambrose. Do I know what the mass of Granny and Ambrose is? Oh yeah, it's this 120. So I'm going to use the same equation that I wrote right here, plus m times v, but that's 240 equals 120, because I'm using this number, 120, multiplied by velocity. How do I get v all by itself? I got to do a little dividing. Divide by 120. This should be familiar to you. Divide by 120. What's 240 divided by 120? Use your calculator. It's 2. 2 meters per second. That's the velocity of Granny and Ambrose after. Okay? Letter E says, even without doing any math, you know that after the collision, the two must, and I highlight that, I emphasize that, must be moving to the right. How can I answer that? Okay, let's try. In the beginning, the total momentum was in the direction of, what was it? In the beginning, the total momentum was what direction? It was to the right, because Granny's moving to the right. Ambrose isn't moving. So in total, it's just Granny that matters. In the beginning, the total momentum was to the right. Oops, sorry, skips ahead. So I'm going to write down to the right. All right. Momentum was in the direction of, the right. Therefore, by the physics law of conservation of momentum, the final momentum must be, well, what does this mean? If momentum is conserved, it stays the same. So if I started off going to the right, I'm going to end going, yeah, it's the same thing, going to the right. So after Granny grabs Ambrose, they both must move to the right. Now you might have thought, Thrasher, it's obvious they're going to the right, but it's based on some physics laws. It's based on this law, the idea that the momentum has to stay the same. That's how you know. Again, here's a good kind of template for the quiz. They might not all fit exactly like this, but notice I'm giving some physics terminology, and then I'm applying it to the problem. Okay, 2 more questions. We're almost done, team. Let's finish up. I got to scroll back up. Oh my gosh, kind of a pain. So number 9, it says the cue ball is moving towards the 8 ball, as shown in the diagram. Afterwards, the cue ball starts moving in the opposite direction. So this is before, this is after. It says this is not possible. This was just like our warm-up. Did you think about that warm-up? So what would you write down? I would mention, well, momentum should be conserved. Again, I'm not writing it down in full sentences. That would take me too long. But momentum should be conserved. So whatever momentum I have in the beginning should be the momentum I have in the end. Well, the 8 ball doesn't seem to have momentum at all. So it just matters about the cue ball. In the beginning, P initial, what direction is the momentum? The momentum is to the right. So after the collision, it should, if momentum is conserved, still be to the right. But look right here. Afterwards, what's the direction of the momentum? It's to the left. Was momentum conserved? No. Oh my gosh. Momentum was not conserved in this example. That's why it's not possible. Okay? I don't have the same right momentum as I ended up with. I should have, I don't know, maybe a situation where we kind of saw this before. Maybe the cue ball is moving. Or maybe it could be something a little more complicated where both are moving. But both of these are more possible because I have momentum to the right. Oops. If I don't have momentum in the same direction, then momentum is not being conserved. Home stretch. There might have been some awkward pausing as I was messing around with the computer, but let's do the last problem. Again, I know it's a long video, but this was optional. Hopefully you're finding it helpful. Number 10, if you haven't read it, read it first. Letter A, I'm trying to fill in the blanks. What's the momentum of this first player? Momentum is mass times velocity. So 100 times 5, use a calculator if you need to, it's 500. What's the momentum of player 2? It's still mass times velocity. What's negative 4 times 75? Can you do that? It's negative 300. If you need a calculator, no worries. There we go. Letter B, what's the total momentum? Keep that negative. What's 500 combined with negative 300? It's positive 200. I'll put the units here so you remember them. Okay, so that's the momentum before they collide. if momentum is conserved, what should the total momentum be after? If momentum's conserved, it should be the same thing. So if I started with 200, I should end with 200. That's how I know what that blank is right there. Okay. Well, it's a tackle. The two are almost together. It's like they're one big object. So what's the total mass? This is like the granny problem. Add up their masses, 75 and 100, 175. Letter E, do a little math. Calculate the velocity of the two after the collision. How could I figure out the velocity? Well, I remember that there's this momentum equation. If I know these two things, I could figure out the velocity. Do I know the mass after the collision? Yeah, remember, it's the two objects combined. So that's 175. So all I need to know now is the momentum of these two objects, and I can find V. What's the momentum? Oh my gosh, we did it! The momentum after must be the momentum before, so that's 200. So how do I solve this problem? I need to divide both sides by 175. So whip out your calculator. What is 200 divided by 175? An answer of about 1.14. I, in fact, had to pause the video because I wanted to double check my calculator. About 1.14. Again, these are tough problems, but the setup is usually the same. Think about the momentum either before or after. That number must be the same. And then our humble, simpler momentum equation is how we're able to solve it. As always, if something was unclear, you could email me. You could go back and re-watch the video, try to listen again. You could ask me questions. All right, but hopefully this video, some of you at least, found helpful to answer these problems. That's it. Thanks a lot for watching.